Hello everyone, today we're going to have a look at what neural networks are, what artificial neurons are, and what type of artificial neurons there are, and how to compose multiple artificial neurons and create neural networks from those. Okay, so the first thing that we are going to have a look at is a bit of history about neural networks. And neural networks were around since the 1950s, and they were first introduced by Warren McColl and Walter Pitts in this paper right here, a logical calculus of the ideas immanent in nervous activity. Of course, the neural networks were initially inspired by the way that we thought that the human brains worked, but as we will discuss later, this was just an initial inspiration, and then on the artificial neural networks are more and more just the computational units. The single, probably most important theoretical result from the neural networks study is the universal approximation theorem, which states that any neural network with a single hidden layer, whatever that means for now, can approximate any function. So you can basically think of any function that you might want to analyze or predict results from that function, and you can be sure that a neural network with a single hidden layer can approximate the results from this function. And one of the first proofs was done in the 1989 for the sigmoid activation function, and we already had a look at the sigmoid activation function, and you should know kinda what the sigmoid is. But more recently, neural networks popularity just exploded with the invention of the deep learning subfield of machine learning, and you might be really interested in different applications of deep learning models or deep neural networks. As you might already know, they are used for images, text, audio data, and whatnot, and they're pretty much conquering all state-of-the-art results right now. So let's have a look at what the original model for neural networks, what was the first model that was developed for the neural networks, and that model is called the Perceptron. The Perceptron is a really simple model which takes as inputs some binary data and produces a binary output from that. It was suggested in the 1950s, so it's pretty old. And for each input there is an associated weight or a parameter, which we call W in here. And once again, the output is just a binary number, so it's 0 or 1. And in order to get the output, we just do a weighted sum of all the weights and the inputs. And if that weight is smaller than some threshold, the result is going to be 0 and 1 otherwise, the output. So let's take for example the decision that you have to make, and this decision is, should you buy a new laptop? And let's say that this decision is based on two features that you think are the most important ones. And the first one is this laptop of color pink, and is it small? So you might think of doing this computation in here, and the result is going to be 0 or 1, and you are going to input your preferences on how important the color pink and how important the size small of the laptop is, thanks to the weights or the parameters of this perceptron. So for example, you can do something even better with the perceptron, and this better thing is to introduce a bias. The bias can be introduced so that we remove the threshold, or we just say that the bias is equal to the minus threshold, so we can rewrite the model in such a way that we use a dot product of the weights and the inputs, then we add the bias, and if this whole expression is less than 0, we can say that again the output of our perceptron is 0, otherwise it's 1. Okay, so we just rewrite the original perceptron rule and removed the need for the threshold that we are going to use. So let's see how we can model the perceptron in TensorFlow and take our example with the laptop and just have a look at how we can use the perceptron model to predict whether or not should we buy a laptop. So to do that, I'm just going to show you the basic template that we are continuously using for TensorFlow.js. And in here, as you can see, I've already imported Plotly, and I'm going to import TensorFlow.js in here too. And then I'm going to define the perceptron model, and it's going to have three parameters: the x, the w's, and the bias. And again, the x and the w are vectors, so we can do a dot product of those. And I'm going to take the dot product using tf dot, and I'm going to pass in the inputs and the weights. Then I'm going to extract the array value of that and take the 0th element. And then I'm going to get the product, add it with the bias, and check if it is less than 0. So if this whole expression is less than 0, I'm going to return 0, otherwise I'm going to return 1. Okay, so to test this one, I'm going to take our example with the laptop and try to call the perceptron in here. I'm going to output the output or the result from that, and the output is going to be defined by the perceptron function, and in here I'm going to input the x's, and let's say that for our example we have a non-ping laptop which is very small, so I'm going to encode that as 0 and 1, and let's say that we think that the color is somewhat important, but the size is really much more important. So I'm going to encode the weights as 0.5 and 0.9, and I'm going to set a bias of minus 0.5. Let's say that you prefer not to buy a laptop than to buy a laptop in general, since laptops are pretty expensive. So if we call this and have a look at the result in our browser, let me open the console. You can see that our perceptron model is predicting that we should buy this laptop, which is not pink, but it has a small size. Okay, so that's pretty much it for the perceptron model. As you can see, the perceptron model is really simple and can output only zeros and ones, and sometimes you want to predict other values except binary data. So for that purpose, we are going to have a look at the Sigmoid neuron. The Sigmoid neuron allows you to input values for the inputs that are between 0 and 1, and uses the Sigmoid function to create a output that is again between 0 and 1. And just for a refresher, here's the sigmoid function. And here is how the sigmoid neuron is defined. Right here. As you can see, we have the sigmoid function, and we have the exactly the same expression that we had for the perceptron model. Okay, so here is the same example that we had in a bit, just above, and the only difference is actually the application of the sigmoid function. Okay, so let's try to define the sigmoid neuron in JavaScript and using TensorFlow.js. Again, I'm going to have the exactly the same parameters that we had before, and this time I'm going to take the product as well, but later I'm going to apply the sigmoid function from tf.sigmoid to the product, and I'm going to add the bias to the product, and I'm just going to take the result from this, take the array, and then I'm going to take the only value in here. Okay, so if we have a look at this result, I'm going to copy this, and I'm going to call sigmoid perceptron. Okay, if we just call the sigmoid perceptron with the exact same data, you can see that the sigmoid perceptron still thinks that we should buy this laptop, but know that it offers us the likelihood or how confident it is in its decision. So it thinks that this is the right decision roughly. Buying a laptop is like 60% is like the 60% correct solution. So that's the first positive of using the sigmoid perceptron model. And the next thing that you can try is to say something like, yeah, it's kind of pink color, by encoding the first element in the x vector as 0.6, and yeah, it's pretty small. And when we compile this result, we're going to have a bit more confident model that this laptop is the right one for us. Since, please note again that we said that it is much more important that the laptop is of smaller size compared to the color. Okay, so we had a look at the sigmoid neuron and the perceptron model, both which are artificial neurons, and we implemented those in TensorFlow.js. Okay, so now that you know about these artificial neurons, you might start thinking, okay, but how do I create neural networks from those stuff? And one way to create neural networks from neurons is to combine those neurons in the so-called layers. And layers are pretty much connections between different neurons, but they're organized in so-called layers or blocks of neurons. And as you can see, the neural network looks like a graph. It's actually a connected acyclic graph, at least this one presented here. And this neural network in here is having two layers, since the input layer is not counted as a layer, since it's just taking in as an input the data. So we have a hidden layer. Here is where the decision is taking place mostly, and we have an output layer, and in here you can grab the result or the output from the neural network. Okay, so how do we first construct those neural networks? Why do they need to be constructed in such a way that it is presented here, and how we can use data to learn, to create, to train neural networks that can be useful for something. So let's say that you want to predict whether or not a laptop should be bought, and if you want to do that, you have to use some data, give that data to the neural network, and there should be some process that allows the neural network to learn which laptops should be bought and which should be skipped. Okay, so we'll have a look at that in a bit, but the most important thing for now in creating neural networks is actually understanding the building blocks that are needed for building those. And two of the most important things that neural networks have to have are activation functions, and we have to have a way to initialize those weights that we've encoded in here. We've encoded those by hand, but when we want to use only data, we have to initialize those parameters in some way, and we have to have some training or some optimization algorithm that finds good values for these. Because imagine you have the data is given from somewhere, but you still have to compute or find some good parameters that are very well at describing the data and making correct predictions in those neural networks. Okay, so let's have a look at activation functions. And the first activation function that you already had a look at is the Sigmoid activation function. And as you can see, the Sigmoid activation function is pretty much defined as this S shape, and values that are roughly -3 or -5 or less are converging to 0, and values that are above 5 or something like that are converging to 1. And in here you have the S shape of the sigmoid. The one main disadvantage of the sigmoid function is again the fact that values that are outside this range, from here onward and here onward, those values, when they're used, the weights in the neural networks during training are becoming closer and closer to 0, so no learning is happening if the weights are 0 in here. You can imagine why this is the case. Okay, so I'm going to show you how you can render a sigmoid function. I'm going to define render sigmoid. And let's have a look at how you can create the x's and the y's for this rendering. So let's first call the render sigmoid in here. And I'm going to define the x's as an array of 20 values. And I'm going to take the values of -10 to 10. So that's why I'm subtracting 10 from the number in here. And for the y's, I'm going to use tf sigmoid. I'm going to input the x's, and I'm going to get an array of that. And then I'm going to call render activation function with x's, y's. I'm going to say that this is a sigmoid, and I'm going to pass in the div container, which is sigmoid container. And if I go to the browser, and I made a mistake in here, I believe. So yep, if I run this, you can see that we have the sigmoid function in here. And as you can see, the farther I go to the right, the closer and closer the result of the y value of the sigmoid function is getting closer to 1. And if I go to the left, it's closer and closer to 0. And only in here you can see that the values are far away from 0 or 1. Okay, so this is the sigmoid function, and again it has its problems because in here and in here the numbers are really close to 1 or 0. The next really probably the most used activation function in when building neural networks is the rectifier linear unit, or the REU. And the REU is linear for values that are 0 or more, and the value, if the input is 0 or less, the output is 0. So as you can see, it flattens pretty much everything that is a negative number to 0, and otherwise you have a linear relationship with the input. So this is a really interesting function, but it has again one disadvantage, and the disadvantage is that it really queues values or put them equal to 0 that are negative. So when you start to train or to learn the functions that you want to approximate, the weights in here are going to be put equal to 0, which means that they are not going to be used during the training. Okay, so let's render the REU function. And then I'm going to have a look at why do we need activation functions at all. Again, I'm going to use TensorFlow, passing the x's, which are the same as the one that I've copied from above for the sigmoid function. Then I'm going to call REU, and I'm going to pass in the REU container. And finally, I'm going to call the function render REU. And as you can see, we have the REU function, and we have zeros for values that are below 0, and then again we have just a linear relationship with the values that are positive. Okay, so before discussing why we need activation functions, I'm going to show you the last activation function that is used very often in practice, and this function is called the leaky REU. And as you can see, if the number that you're passing in as an input is positive, it's exactly the same as the REU function, but negative values are just flattened but not put equal to 0. And how much are they scaled or flattened is controlled via parameter that you can pass to TensorFlow.js. So for this example, I'm going to call a function render leaky REU, which I'm going to define in here. And again, I'm going to copy and paste everything from here. And I'm going to say that I want the leaky REU container. And if everything is working, we should see the leaky REU in here. Okay, so here it is. And as I already told you, you can pass in a second parameter, which is, let me just have a look at the documentation, is known as alpha. So the default value for alpha is, I'm not sure what it is actually. Let's have a look at the documentation, the API. Okay, tflick.ru. The scaling factor defaults to 0.2. Okay, so if I change this to, let's say, 0.6 and recompile the example, you can see that the values are not that well scaled. And if I say something like 0.05 and compile again, you can see that the values are much closer to 0, at least initially. So you can play around with this parameter too when creating your neural networks. Okay, so we haven't discussed why do we need activation functions. As we've already seen, the need for the activation function in the perceptron has came from the fact that the original perceptron model only could have outputted a binary values, and those binary values are not enough to approximate any function that we want. So if we want to approximate functions that are not linear or can be expressed via some linear combinations, we have to use those activation functions to introduce non-linearity in our neural networks. So in this way, our neural networks can really approximate any function and not only linear ones. Okay, so that's why we need activation functions, and different activation functions allow us to train our neural networks faster and to be more accurate. But sometimes you have to experiment a lot with what activation function is best for your use case. Okay, so the last thing that we are going to have a look at is the weight initialization. And during training a neural network, we are going to use optimization algorithms that are going to search for those parameters W's of our models, and the algorithm that is used to find those parameters is called stochastic gradient descent, and its job is to find good parameters. Those parameters should be found in a way that there is some objective function or something called loss function or error function that is actually evaluating the current parameters and using those to predict the values from the data that we are putting in. And if those values are good, or if the predictions of our model currently are good, the error function is going to return a low error. And if those predictions are bad, the error function or the loss function is going to return higher values. So based on that, the stochastic gradient descent algorithm is going to know that it is performing well or it is performing badly. But we need some initial values for the weights, since the stochastic gradient descent is using those weights for its starting point for the search that is going to be using. So one natural assumption might be that we can be maybe initializing those weights with zeros, and that will be a really bad idea, because if we initialize the weights with zeros, that will make multiplication any number that the stochastic gradient descent finds with zero. So we would have all weights in our neural network equal to 0, and for that matter, any constant value will result in non-updating the weight or the parameters in a way that it is towards finding better parameters or better values for those weights. So if you want to initialize your weights, please don't use constant initialization, so don't put every weight equal to some number. And then again, if you if you want to start with some good values, you also can't use too small or too large values for the initialization. Why is that? Because once again, the stochastic gradient descent is a random algorithm and works with gradients. Using too large or too small values will make the weights increase or decrease exponentially, and once those weights are too small or too large numbers, weights don't matter. They don't learn, they don't get updated, and the neural network is not going to learn anything. And the last thing that is pretty much used universally is to initialize the weights with some small random numbers, and those small numbers are usually drawn from a normal distribution with a mean of 0 and a standard deviation of 1. At least that's one of the first ways that we've used to initialize the weights. But more recently, in the last couple of maybe 5 to 10 years, there were an explosion of ways to initialize the weights of our neural networks. And as you can see in this link right here, TensorFlow.js is having a lot of initializers. Let me just... Okay, so we have constant, Gorod, normal, uniform, LeCun, etc., etc. You have a lot of initializers that you can use when creating neural networks using TensorFlow.js. And I believe that the default initializer is the Gorod normal, also called Xavier normal initializer, and it's defined as such, and there is even a link to the original paper for the initializer, so you can have a look at it. Okay, so that's pretty much what you need to know about building a neural network, and in the next video I'm going to show you how to construct one using TensorFlow.js and solve the problem about whether or not should you buy a specific laptop based on some data that we have. We're going to train the neural network and use it to predict whether or not should you buy a laptop or not. Okay, so thanks guys. Thanks for listening and watching this video. The complete source code is going to be linked in the description below, and please subscribe, and thanks for watching. Bye bye.